Hello, everybody, and welcome back to our physics engine programming. We are programming a physics engine from scratch using C# and monogame. And I hope that in following along with this endeavor that you are learning new things. I hope that we're able to gain knowledge from doing this, and I hope that we're able to find utility in this as well. So recently we've been finding the contact points between the shapes that are intersecting. There's basically three different cases. We found the first two. The first two were the circle-to-circle contact point, the circle-to-polygon contact point, and today what we're going to work on is finding the contact point or points. There could be 2 points between 2 polygons. So the source code is freely available. It's going to be in a link in the description below. So let's get to working on finding the contact points between 2 polygons. I drew up some diagrams, and these are going to indicate basically what we're looking at for the problems we need to solve. Now, at the heart of this algorithm is going to be the same function we created in the last video, and that's the point line segment distance formula. And if you want to know more about that, there's a video on this channel where I go in depth about how that works, and we also implemented it in the last video. But I will link to that video so you can take a look at that if you want to know how to find the distance between an arbitrary point in space and a line segment in two-dimensional space. But I drew up some diagrams, and these indicate all the cases that we need to handle. So the first one is the most simple. In this case, the polygons are oriented in such a way that there's only one contact point. And we can see that's this one here. So the basic idea of this algorithm is we're going to loop through all the vertices in one polygon. So we'll just start with polygon A and compare those vertices to all of the edges of the other polygon, so polygon B, using the point line segment distance formula. And so in this case, if this is vertex 0, we're going to compare that to this edge, and then this edge, and this edge. And then we're going to find the closest point between all of those edges or line segments. And in this case, that closest edge would look something like this, and the closest point would be right there. And we keep doing that for every edge and find the closest one. Now, once we loop through all the points in polygon A, we're going to find that the closest point is this one right here. That'll be the closest distance. And it looks something like that. But we obviously have one point that is closer, and the way we find that one is now by looping through all of the points in B and comparing those to the edges of A. All right. And so if this is point 0, and we go around in clockwise ordering, we'd find that the closest point on A is going to be right here to that one. The closest here would be that one, the closest here would be that one, and the closest here would be that one. And so as we loop around, we're just going to find the minimum distance, the point with the minimum distance to the other polygon. And that would end up being this one. Now, this is the simplest case because there's only one contact point or one closest point between the 2 polygons. Now, the other cases are going to look something like this. Here we have a case where each polygon has a closest point. Polygon B has a closest point right here, and polygon A has a closest point right here, in which case we're going to save both of those points as contact points and use those points to resolve our collisions. But the algorithm works exactly the same way. We loop through all the points in one and compare them to the edges of the other, and then loop through all the vertices in polygon B and compare that to the edges of polygon A. The difference being here is that we're going to compare the distances. And if we ever find 2 distances that are exactly the same, or I guess in reality, they're really close to being the same. Because of floating point inaccuracies, we're going to have to test to see if they're close or close enough. But if we ever find 2 distances that are close enough to being equal, we're going to then save both points as contact points. So we'll have contact point 1 and contact point 2. The other 2 cases look something like this. So in these cases, both contact points are found in one of the shapes. So in this case, they're both found in shape B, and in this case, they're both found in shape A. But in all cases, the algorithm works exactly the same. We just loop through all the points in one and compare it to the edges of the other and find the absolute closest distance. All right, so let's go to our code and let's go ahead and implement this. Let's see, right now we're in the game class. Let's move over to the collisions class. Here is our find contact points formula. Now this is the main entry point where we find the contact points. In fact, let's go back to the flat world and let's review what we're looking at here. So in our collision step, We're looping through all of the bodies and detecting collisions right here. Once we find a collision, we are moving the bodies apart. And then we're finding the actual contact points right here with this function, find contact points. And let's go back to the collisions class. So that's this function right here, find contact points. And we've implemented all the cases except for one, and that's the polygon to polygon case. And in this engine, those are boxes right now. Later on, we'll probably look at moving that to general case convex polygons. But right now we're using boxes. So if we have the case where both shapes are boxes, let's implement find contact points. So I'm going to scroll down here and I'm going to make one more function, and I'm going to call this find contact points. So the information we need to pass into this function are going to be the transform vertices for each polygon, and then we're going to pass out the 2 contact points and also an integer indicating how many contact points it found. And this will either be 1 or 2. All right, so let's pass in the transform vertices for each shape. All right, so now I'm going to pass out the actual contact information. So these will be the 2 contact points. And then finally, one last value that'll indicate how many contact points we found. And this will either be 1 or 2 contact points. We'll just call it the contact count. All right, and let's just drop down these arguments to the next line so we can read them a little bit easier. All right, so inside this function, let's define some default parameters for our out values. Okay, so what we're going to do now is loop through all of the vertices in one and compare that to the edges of the other. So let's just loop through all of A and compare that to the edges of B. All right, we're going to go ahead and get the current vertex that we're on inside vertices A, and I'm going to call that point P. So now we're going to have an interior loop where we're going to loop through all of the edges in vertices B. Oh, and up here I did not define vertices B as an array, so this is an array of flat vector. Okay, and inside this interior loop, what we're going to do is we're going to find the edges. We're going to get the 2 points that define an edge. So we're going to start at J. So let's get flat vector. I'm going to call this VA. So this is the first point on the line segment we're testing. And that'll just be the first vertex in B, or whatever vertex J is currently. And then the next one is just going to be the next vertex in B. I'll call that VB. And so from vertices B, we're just going to get J plus 1, but there's a possibility that we get to the end of the array with J plus 1, or we get past the end of the array with J plus 1. So we're going to mod this, or use the remainder operator with the length of vertices B. Okay, so now we have a point and we have an edge. Let's call our function to find the closest point between a point and a line segment. Okay, we're going to pass in the point and then the line segment endpoints. And then we'll pass out a distance squared and then also a closest point. All right, so that's the most basic part of the algorithm. So now what we want to do is some comparisons. So now we need to do the logic or find the actual closest point or points on the polygon. And I need to save a value for the minimum distance that we found. So let's, outside the loop, create a min distance squared. And we'll just set that to the floating point max value. Basically what we're going to do here is we need to do a couple of checks. Now let's start out with the easiest check. So the easiest check is if we found a distance that is smaller than our minimum distance, then we're going to save this as the minimum distance, and that's going to be our new contact point. So if the distance we found is less than the min distance squared, that means we have a new minimum distance. And so we're going to save the new minimum distance. In this case, if we found an absolute minimum distance, that means we only have one contact point. So if this ever happens, we're going to set the contact count to 1, and then we're going to save the actual contact. So contact 1 is going to be equal to CP, or that's this value that we got returned right here. Okay, so this is the case that looks something like this. We found an absolute minimum distance, and every time we find a minimum distance that is less than every other minimum distance, we reset, and we reset the count to 1, and we save that as the absolute only contact point. There's another case that we have to check for before we actually do this. This is the simplest case. But before we do this, I have to make another if statement. And I need to determine if the distance that we're getting is actually equal to our minimum distance that we've saved from before. This means that we found another point that is a minimum distance, in which case we're going to have two contact points. If the distance is not equal to the minimum distance, meaning we don't have two contact points, then the other check we're going to do is if the distance is less than the minimum distance, in which case we have one contact point. So first we check to see if the distances are equal, if the new distance is equal to our minimum distance. And if that's not the case, otherwise let's check to see if this is a new minimum distance. So now in this case, if the distances are equal, meaning we found a new contact point which is the same distance as our minimum distance, that means we're going to have two contact points and we need to save that contact point. In this case, what we're going to do is now set the contact 2 equal to the contact point that we got. And then we're going to set the contact count equal to 2. So now this is almost done. There is actually one more case that we need to handle. Now this case is kind of a tricky one, and it took me a little bit to figure out. But let me draw what it looks like. All right, so there is one case. Let me draw two boxes here. There's a case, there's a possibility where we have two boxes that look something like this. Okay, and this case is kind of a tricky one, and it took me a little while to figure it out. But what happens sometimes is you have 2 points on different polygons that are in basically the same place. And if they're in the same place and we're using the logic that we have currently, it's going to go ahead and wipe out this point as a contact point, and it's going to save this one as the only contact point. And there's a chance that if we do that, it's going to wipe out other information. So let me go ahead and get rid of this. Let me rename these polygons. So let's call this one A and this one B. What's happening here is if we loop around all of these vertices and find the two closest points, we're going to find that that's this one and this one. Now we're going to loop through all the vertices in B, and we're going to find out that there is a new closest point right here. And actually, this one is exactly the same as this one. And I won't say exactly, but they're close enough to being in the same place that they're basically in the same two-dimensional space. There's a possibility that this new one in B is going to become the new contact point and then wipe out our old contact point information. And we don't want that to happen. But what we want to do here is if we find a contact point that is also a minimum distance, but is in basically the same place as an already found contact point, then we want to disregard it because we've already found a contact point in that same location, and so we don't need to find another one. So right here where we found a distance that is the same, we need to check to see if the contact point 1 is already in that same place. So the check will look something like this. If the new contact point we found does not equal contact 1, then we know that this is a new unique contact point, and we can then save it to contact point 2. Now, we don't have a does not equal or a equal function between two vectors. And we're going to solve that here by actually solving another problem. So the problem we're going to run into with this equal sign and this not equal to sign is that we're comparing floating point values. When you compare floating point values with equals, you have to be really careful because of the inaccuracies that can be involved with floating point values. And usually when you're comparing floating point values for equals, you want to test to see if they're close enough. So we're going to make an actual function that's going to take care of this equals for us and determine if the two floating point values are close enough that we're going to consider them equal. So let's go back to our flat math library. I'm going to make a couple of functions here. So the first one's going to return a Boolean value, and I'm going to call this nearly equal. And we're going to give it two floating point values. And now in this engine, the way we're going to consider two objects close enough to being equal is if they are less than 0.5 millimeters apart. So we're using meters as our base value. So every one unit, every one floating point unit is 1 meter. So we're going to use the value of less than half a millimeter to indicate that these values are close enough that they are equal. And the way that looks is we subtract the two values from each other to see how far apart they are. All right, and then we need to get the absolute value because it's possible that we get a negative value here. And then I'm going to compare that to some very small amount, and that is half of a millimeter. In fact, let's go up to the top here, and I'm going to make a constant value for a very small amount. So 1 would be 1 meter. 0.1 would be a tenth of a meter. 0.01 would be a hundredth of a meter or a centimeter. 0.001 would be a millimeter. And then 0.0005 would then be half of a millimeter. And then we'll just write a description here saying, okay, there we are. So now we have a constant value that is a very small amount that is equal to 1/2 of a millimeter. So we'll scroll down here and we're just going to compare this. So if the absolute value of the distance between these floating point values is less than a very small amount, then we'll consider them equal and we will return the result. And actually, instead of returning the result like that, let's just return and get rid of the result variable. So now I want to do the same function, but I want to do it for vectors. Okay, I want to determine if two vectors are really close together, or basically equal in position. So we'll give it the same name, but we're going to pass in two vectors. Okay, and what we're going to do here is just use this nearly equal function up here with each of the components. So with the x component and then the y component. So let's return if the x components are nearly equal and the y components are nearly equal. So if each component, the x components are nearly equal and the y components are nearly equal, then we're going to consider that these two vectors are in the exact same place and we return true. All right, back in our collisions class, let's replace this equal sign with the nearly equal. And then this not equal sign, let's use the nearly equal function there as well. Okay, and then we're going to pass in the two vectors. And I need to reverse this, so I need to put the not sign in front. So let's go ahead and take a look at this now. So first of all, we determine, is the distance squared nearly equal to the minimum distance squared? And then, if it is the contact point we're passing in not already equal to the first contact point? So that is all of the logic we needed to implement. We just need to do this same loop, but in reverse. So now we need to loop through all the vertices of B and compare them to the edges of A. So we're just going to copy this whole loop right here. We're going to do it again, but in reverse. All right, so let's copy that. We're going to paste it right in here. And so now we're just going to change vertices A to vertices B. Okay, and then vertices B is going to be vertices A. Okay, and with that, we should now be able to get all the contact points between two polygons. Let's go back to our collisions. Actually, let's go back to our flat world. Now this contact points function, find contact points function, should be complete. And without us changing any more code, we should get all the contact points. So let's go ahead and run this and just make sure it's working like we think it should. All right, so I'm going to drop a polygon into this world here, or one of our boxes, and we should end up with two contact points between this ground polygon and the new one that I passed in. Okay, so that is not working. Let's take a look at why it's not giving us the points. So back in our collisions class. Oh, okay, and all right, so here's the problem. I have a typo right here. Here's the loop where we're going through all of the vertices, and we're using I as the indexer. In the second loop, we're using J as the indexer, but when I get over here, I'm actually incrementing I instead of incrementing J. So we need to increment J right there. And let's scroll down. I think I need to do the same thing. Yep, down in this loop. So we are incrementing I instead of J. So let's go ahead and change that to J. So typo there. Now we're looping through I and incrementing I indexing j and incrementing j. Okay, so that should work. Let's go ahead and run that and make sure it looks like it should. Okay, let's drop a polygon into the world. All right, and actually there's one more thing I forgot to do, and this is probably the most obvious thing or the most simple thing to correct. So now that we've finished this find contact points between polygons, I actually need to throw the function into our other function where we're comparing the shapes to find the polygon and the polygon. So in the case where we have two polygons, let's actually call the function for find contact points. So the contact points, we're going to pass in the transform vertices for each body. So we're going to get body A. We're going to get the transform vertices, and same thing for body B. All right, and then let's pass out the contact information. So we're going to pass out contact 1, contact 2, and then the actual contact count. So once we pass these values out, they will be passed to these parameters here, and then pass back out to our world class here in the form of contact 1, contact 2, and a contact count. So now that we have that, let's run that and make sure it is working like we expect. Okay, there we go. So it looks like, there we go. So we have the two contact points there between the two polygons. Let's stack some up here. We're getting those two contact points. And zoom in a little bit and see what that looks like. Okay, and that looks exactly right. It looks like we're getting all the points according to how they should look. So now we found all the contact points between all the different shapes. And what we're going to do next is start working on rotational physics. All right, so now that we have the actual contact points in space, we're going to work on rotational physics. And so we're going to have to start getting things like, calculating things like inertia, or how much does this, so inertia is basically how much does this object resist rotation? And it's based on the mass and the density and all that, but we'll talk about that in upcoming videos. But that's how we find the contact points right now. And before I turn this video, before we move on, I want to change the way we're displaying our contact points. So if you go back to the game class, I want to change the color, and I also want to give them an outline so they're easier to see. So here's the draw method, and we're drawing the contact points right here. So I'm going to change this to red. And then I want to give the contact points an outline, a white outline. And then I want to shrink them down just a little bit. So let's give them the outline. We need to pass in this same contact point. So instead of calling this again, let's move that up here, and I'm actually going to save that contact point. Okay, we're going to pass in the contact point position to these functions. And the size, I'm going to make this 0.3 for each. So we were using 0.5 as the size. I'm going to change it to 0.3, and then give the outline a white color. All right, and let's just see what that looks like. All right, that looks good. Okay, so to me, they're a little bit easier to see this way, and I like that they're smaller and outlined like that. Okay, so there's the contacts. So there we're finding the contact points between two polygons. Let's put some other objects in here and just see how everything looks. All right, so based on the way this looks, and I'm seeing all the contact points in the correct locations, it all looks good. All right, so now we have the contact points between all of our shapes. Let's move on to rotational physics.